Next up, Sauli Kiviranta from XRTC is going to talk about, well, I'll let you explain it.
Yes, I hope you can hear me. All good? You can hear me? All right. So I went up there all the way to the application layer. I came back, survived to bring you the news. It's not all bad news, but one thing is that it's not the layer 8 problem. So it wasn't the users. It was something else, and I have gone to the Brazil, to the automotive industry, North America, Canada, to the forestry, Australia, mining, Japan, media, Europe, all the way to the seas, as well down underground in the mines. And this is what I want to share with you today in this talk. So, death from above. It should be telling sign about the presentation. A little bit of background, I'm Sauli Kiviranta, the CEO of Delta Signi Labs. The company itself is a VTT spin-off company, so I'm not a network engineer. I just ended up dealing with a lot of problems related to trying to run some traffic over the networks around the world. As I mentioned, I have been dealing with various different use cases and business cases, and usually those where you get boots on and you get hands dirty and you are somewhere in very, very remote location. And of course the requirements are that you have to have some live streaming or audio, live audio, or some other control signals coming, so it's a fun combination. But today's talk started at VTT when we were dealing with European Space Agency, how to support the astronauts into clean rooms when there's satellite assembly, but also to the International Space Station when you might have some issues and the flight ticket is a bit expensive, you don't want to always go there. That how the ground control can actually support the guys up there. And this is what we did with ESA, mostly with the geostationary satellites, investigation, what happens on the application layer, and what is it that we can do from ground to up there. Turns out we have a lot of issues on our way. It's a multidimensional problem. We have the weather effects that hit us back, especially with the satellite links. We have the distance, sometimes absurd. Let's say geostationary 40,000 kilometers, or you go to Australia to a mine, it's like 10,000 kilometers plus. We have obstacles. It might be a container handling equipment somewhere in a harbor. You cannot do the radio design. They put some metal objects here and there. In mining, you are exploding tunnels, building up the network, and you can never quite nail the radio design. And then you have, of course, everybody else also on that same network where you are trying to do your job and they are trying to do theirs. And of course, there's always the motivation to say that my traffic is far more important than your traffic. And some elbowing starts to happen. And of course, today interference is one thing. But just like generally for the audience, if I make a claim that 1% packet loss reduces the throughput up to 1,000 times. Is this credible? Anybody finds this credible? That's a very, very good remark. It's of course, you are worried about the latency product there, but in some cases it can be down to 1,000 times reduction, and we will take a look at that. But let's get back to the basics of the application layer and where I'm looking at the networks that you are hosting and the bits are running over your infra. This is the classic picture what we see in the school when we talk about TCP. Today, still most of the traffic, at least most of the applications, Quick is kicking in there, but most of the applications are still running on TCP. And then you have the maximum bandwidth. We are maybe a little bit further away from the base station. We are a little bit less physical. Even the laws of physics allow us a little bit less bit rate. We go a little bit closer to the base station, we might have a little bit higher bitrate theoretically, but what the applications see, what the TCP transactions see is of course the classic sawtooth. Shape might differ depending on the consistent control algorithm, but the basic principle is the same. And what this creates, the headache that it creates, that it's only ever going to be some average that we get out of that consistent window. And in the school books, when we see this picture, you don't get the impression that it's 1 to 1,000 ratio. It tells you a very rosy picture about what is actually happening in the TCP transactions. And that is the problem. So let's take a look at this video, short video. So we are running on a gigabit fiber. We just use third-party tool. Check that yes, we have 1 gigabit. The browser and the fast.com by Netflix is able to see about 1 giga from the channel. We use Netropy, Apposite. NASA is using, for example, for Mars and Moon missions, the Apposite for link conditioning. And we put 1% packet loss and 100 millisecond round trip time. So from Europe to about North America. And you saw that it drops from 1 gigabit to only 3 megabit per second. And even that is a lie because fast.com is using 8 parallel channels in this test. So this is not your typical REST API transaction. But the good news is that we can do something, and that's what we do, that's our business. We are trying to help those applications to see more of the bandwidth, what is there available, what you have provided, so that the application layer is not lying. You sold them 300 megabits per second, and that's reaching the contract. They run speed.com, they run iPerf, maybe even fast.com, and they should see that. What we are doing is we are trying to make sure that even in lossy conditions, where we are at the sea with geostationary satellite or Starlink, or some other corner case, some private 5G somewhere in the mine or the harbor, that we can make more of that bandwidth available. Here we are demonstrating that we can make it 10 times more. That's pretty cool, but you remember the upside is in this case 300x. In most cases it's that 1000x. What we are aiming for. So it is death from above. We have gone from 1 gigabit per second with just, if you think about 1% packet loss, it's like your typical consistent base station in the afternoon. You go home from the work, you boot up the Netflix, you relax, and you try to get the streaming running. That's where you get 1% packet loss, to give you some kind of reference. Geostationary satellite, of course the latency is like up to 800 milliseconds. You might go some 5% packet loss. Or if you are on Starlink, it might be during a storm, very severe weather case, it might be up to 10% packet loss. So there are cases where you are exposed to far, far bigger packet losses than just 1%. Many of you, how many of you are commuting with the train? Quite a few. Okay, I have some news for you. Not good news. All right. So what happens? Why those numbers look so horrible? So on the left side you see this pattern. Blue bubble is a REST API transaction, and the green bubble is when it was completed. So sometimes you see that those bubbles are quite close to each other, and this is when you get lucky. You open the Facebook, refresh it, and it opens. So you open Helsingin Sanomat or some like media-heavy site, and you get lucky, and it just opens up. And sometimes this loading spinner pops up, and you're cursing your life. Like, how is it possible? I have the 300 megabit contract. And that's what happens when you see the step going up. It's multiple seconds, and it's just a statistical question that how unlucky you get with the consistent window. And it's all networks. Here we have some example from mining industry. In Pyhäsalmi mine, there was just a stop of a 2G network for some IoT devices there. We run some tests, sometimes 10 kilobit per second. Luckily, we were able to squeeze a little bit more out of it, so we can still fix things and do some things a little bit better than that. Here is another example where we have some good results that actually have some financial value with Roima. They are dealing with PLM systems and ERPs, and you can imagine being a very, very senior designer trying to do your CAD modeling for some site or machine and staring at the screen half an hour, 45 minutes, going to cook some coffee, come back with after 3 cups of coffee and still loading. So that's the reality of application layer. After all 5Gs, everything what we have, that's the reality, that's the death from above. And with some nice optimization on the application layer, we have been able to improve, for example, small file transfer, 6 megabytes, 7 times improvement, 80 megabytes, 11 times improvement. So we can do a lot of good stuff and a little bit alleviate the pain. Then if it comes to the video cases, the consistent window is really the thing that kills everything, especially for TCP. When the consistent window shrinks at when you have some packet loss, it can be sometimes like just few tens of kilobytes. And when you have a keyframe in a video stream that can be like up to 200 kilobytes, let's say 4K video, keyframes can be 250 kilobytes, That's where you have head of line blocking, and then is the question how much round trip time you have the server, how much you have to wait for the acknowledgement before you can flush the next frame, and this is the issue where you never see TCP being used for real-time video, and that's what the school books say, that's why they say go UDP, if it's real-time, go UDP, but that's not exactly true, and now you have a little bit of understanding why it's not absolutely totally true. Here is another video clip, what we can do. This is TCP. So AWS server in Australia, webcam in Finland on 5G, round trip ping is about 300 milliseconds. So that's as fast as you can go. So here we have just the same TCP with a little bit of a spices on top, a little bit of a parallelism, and then below you see the classical TCP. Let's play it again. So you left is the local playback from the webcam, top right is the what we do, accelerated TCP, and below is the classic TCP, how is today. Why the school books say that it's simply not possible to use TCP for anything real time. So what can we do with the video? Benchmark is Barrick. We were working with Barrick. It's a big mining company on the Pyhäsalmi mine. And their question was, they have companies like Sandvik and Epiroc delivering mining machines, and they want to have remote operations because it's very difficult to get people to the mines. You want to have as much as possible equipment remotely operated, and their benchmark is 1 second delay. So if you think about mine and 1,000 kilometer distance from the mine, you can draw a circle around any mine, and you can think that, okay, how many cities are within that circle where you can possibly recruit a guy who can operate a mining loader. Very restrictive. So what we were able to demonstrate that we can bring that benchmark delay, what you just saw, that it's 300 milliseconds, very close to ping, with operational distance up to 10,000 kilometers. So really like follow the sun, you can have mining operations in any continent, and from any remote operation in those continents you can cover any of the mines in the world. So that already has a financial value. So this is the issue what is there, regardless of the network, that we buy the 300 megabit connection. We say that it's roughly that. We run some speed test, let's say iPerf even, and it gives us maybe 90% of the channel, but the reality of the application layer is that it's sometimes like a small fraction of that the application will be able to see. And then for the guys who are on the VR, sometimes trying to work, remember 1% packet loss, that busy afternoon in the city, 5% packet loss in the geostationary satellites, 10% packet loss on the LEO satellites during a storm. The worst possible condition that is known to humanity today is the VR train Wi-Fi, up to 30% packet loss. So no wonder you are struggling. Okay, we will measure that. And of course, like this is the desperation. You saw probably news, was it last week or 2 weeks ago, that they have launched a 2 years project, cost more than 2 million, to shoot lasers through the train windows to be able to propagate mobile signals better through the windows. So this is the level of desperation, that solving problems just purely with the hardware. So that you are trying to shoot holes to the windows. I'm not joking. This was in the news. VR has commissioned 2 years, 2 million plus project to shoot holes to the windows, and the problem is at the application layer. That's the issue. That's the issue that is constrained everything. So that's it. That's my message to you. Yes, invest into the hardware, but sometimes ask the question what is happening up there at the application layer, and sometimes you might find that it's very troublesome. And we are there to help those issues and a little bit educate and propagate the news from up there. Thank you very much.
Are there any questions? There's one.
So I was wondering if you have looked into combining with forward error correction.
Yes, of course, that's a very smart move to do. And TCP has this advantage that we can pay with time, we can retransmit things. Let's say that we are 10 milliseconds away and our deadline for some real-time application is 100 milliseconds. So that's the time that we can pay with the retransmissions, but that's not always enough. And then you have the same what the UDP has, that you just have to fix that remaining long tail of delay with the FEC. So absolutely, it's a fundamental solution. Let's see that I'm brave enough to make a live demo. Let's see how it goes. It's always an exciting moment where you're trying to do something live. And this is I immediately spoiled this whole demo because we have a small Easter egg here at the customer site. We are using this Christmas village in all our demos, especially in our lab, for video cases, because it has continuous rotationary motion, which is humans are very sensitive for continuous rotationary movement. When there is even one frame missing, you always recognize it. And moreover, it enforces the encoders to generate delta frames, because otherwise H.264, for example, it converges to 0, and it's not very useful for us to develop systems because there's nothing like today in this demo setup. But where we actually are in this demo is we are now in the Pyhäsalmi mine in Kallio. So we are going from my laptop over the Wi-Fi all the way to Sweden AWS. And from AWS in Sweden we are going to Pyhäsalmi mine, some 300 kilometers north from here. And inside the mine we have just the COTS axis camera, and we are connecting through this Wi-Fi access point with the camera. So 2 radio hubs, Wi-Fi inside the mine, go all the way to Sweden and come back. And this is the barric we were using for Normet for remote training and testing different scenarios. And as you can see, there is not always mining cars going around or people walking around, so we had to install this Christmas village to force some changes delta into the traffic, video traffic. So that was one demo. Let's push it even more forward. Let's make another demo. Let's go to Australia. See how this goes.
Was that previous with or without your solution?
It was with. So all is just pure TCP traffic. So let's try to go to Australia and back and see what happens. See what happens there. If we get the view back or no. So at least we are seeing the server, which is a good sign. Let's see if we can get some traffic coming back in. Okay, so at least something is coming even from Australia. But you roughly get the idea that what is the difference between just the classical TCP and why people are saying that it's not very suitable for real time traffic. So that's it. 2 live demos. They actually work. I'm very happy. Thank you, everybody.
2 live demos, but no demo effect.
Yeah.
Any more questions?
What are you doing differently compared to like WebRTC, Quick, and so on?
WebRTC is interesting because it has been like last almost 30 years, 25 years, the workhorse for all real-time data, and of course XRTC is just a play of words with WebRTC. So WebRTC, Norwegian startup, developed it for web applications, and it has been doing like a lot of good work. But now it starts to be at the end of life, and our message is that we want to be the generic version of that. Even if our transport is TCP, we want to be able to make all applications real-time, and really what we really want to achieve is squeeze out the performance that is visible at application layer so that we can enable various different real-time use cases. Of course, Quick has been under development for like 8 years to replace WebRTC. It hasn't yet hit any of the benchmarks that it would solve the problems. It has a lot of complexity issues, so I would say that Quick is maybe like equivalent, but at least what our message is that this is now works out there on the world and is completely use case agnostic. Doesn't care if you want to do a file transfer or video or audio signals, control signals. Cool thing about this demo, especially the Pyhäsalmi mine demo, is that it was the full control loop. So the PTZ camera, we were just from here, from the trackpad, moving it around and getting the stream. So technically it's exactly the same like you are operating a mining machine or remote operating drone somewhere in the battlefield. Yes.
So do you anticipate any uses for this for example, in applications like news gathering where you have high quality MPEG-4
Yeah.
HD video streams from the field?
Yes,
with
absolutely.
with also multipath, like multiple different say mobile.
Cool thing with the TCP is that we inherently relay all the traffic through a server. So depending on where we want to put the server, we can have the control loop that the remote operator can have, for example, certain benchmark for milliseconds, that they need to have the stream in 200 milliseconds. Then we can a little bit spice it up, have quality up for FEC. But at the end of the day, the control loop has to be 200 milliseconds. So we for example, in the video traffic, we just start to drop frames and say that we just hit the, but the cool thing with the TCP is also that there will be the machinery of retransmission happening behind the scenes, and that long tail we can then tee to some other service that, for example, can just then archive all 100% of the frames that was ever sent. So these adjacent consumers like AI, it's like collection of data for AI. Like what maybe is the message for you that we saw this catastrophic situation that like multiple subsea cables were cut off and the traffic was happily going on. It's because of these reasons why there is so much slack in those optical cables. But soon, hopefully, we will be contributing to it. For example, AI data collection, every single machine is able to collect that data. That's the question that NVIDIA and Nokia, what they ultimately want to solve at the end of the day, how to enable the data collection for training the AI models. It's not possible today. We want to make it also possible on our behalf from the software perspective. But then once you have trained your models, how do you do the inference? A lot of machine vision tasks today, for example, in food industry, in process industry, you have to bring the compute to the site. You might have massive server racks inside the mine, middle of nowhere, and that's completely insane. What you want to do is you want to have a reliable signal coming from the site to the closest server. You want to do the inference there and close the feedback loop and make the decision about the process based on that. So all this will come and will start to saturate all those infrastructure that you have built, hopefully. And this is how we see how things are going to change. So.
Any other questions?
I will be hanging around for the sauna for the evening, so feel free to come ask questions also afterwards.
Okay, so give Sauli another big hand.
Thank you.